Hello and welcome to the next video in our Essential Skills series. These videos aim to help you to prepare for Paper 1 Physics, but also to understand the skills behind the science much better. I'm Dr. Derek Fish, Director of Unizulu Science Centre at the University of Zululand. This is video 4.1 on Ohm's Law and Circuits. You'll find it from pages 20 to 25 in your booklet. But before we get to page 20, let's have a recap of the introduction and start in page 3, just so we can see properly where we are. Remember, the page number will always be in the bottom right of my screen. It's on the top right of your page. So we're still looking at the essential skill of graphs. And after the introduction, we're looking at 4 applications. We've done motion graphs, photoelectric effect. We're now looking at Ohm's law. We specifically want to do an experiment that produces a graph of current against voltage and understand how to look at that graph. Once again, the examiners comment that the interpretation of graphs and graphing skills is a challenge for many learners. So we take that seriously. On page 4, obviously this falls under electricity and magnetism, and it spans all 3 years. In grade 10, you're introduced to electric circuits. Grade 11, more about electric circuits, your energy and power equations. And grade 12, internal resistance will be the subject of the next video, but there are prescribed experiments all the way through that produce the graphs that we're going to look at. So please don't forget your grade 10 and 11 work. Again, the examiners comment that students showed little evidence of having relearned their grade 10 and 11 work, especially Ohm's law and your power and energy equations, your circuit calculations. So electricity is one of the larger sections in your exam, counting about 1/3 of the marks in your exams. And Ohm's law, if it comes up, will be under question 8 on electric circuits. So typically that's about 19 marks. That's the average for the last 3 papers. Now there are 3 electricity questions. Question 7 deals with electrostatics, Coulomb's laws and electric fields. Question 8, or sometimes it's question 9 in the older papers, deals with electric circuits, may or may not have internal resistance. Question 9 deals with electrodynamics, motors, generators, and alternating current. Looking on page 5 at the skills required by the CAPS curriculum, changing the subject to the formula, the specific example they give is Ohm's law. And obviously this is pertinent to this video. Rate, direct and inverse proportion, and then of course all your skills under number 10 for handling data and graphs. So let's remind ourselves of graphs, and this will be found on pages 6 and 7 in your books. Remember, a graph can have 3 functions, and the Ohm's law graph is a relationship graph between the variables current and voltage. It's a linear graph, it's not a curve, it's quite straightforward. When you come to draw a graph on page 6, we taught you this Talsup method. I'm just pointing out that it is there on page 6, and we will use it in our Ohm's law experiment to draw the graph. And it's much better for me to explain it to you while we are using it. Otherwise, go back to video 1.2, the introduction to graphs. Now, it's very important that we understand the mathematical nature of the straight line graphs. A straight line graph has 2 variables, y and x. Y is the dependent variable on the vertical axis. X is the independent variable on the horizontal axis. X is the one that we will directly change. In this experiment, it will be voltage. And y is the one that will be a result of this. In this experiment, it will be current. Then there are 2 constants. C is the y-intercept, where the graph cuts the y-axis, and m is the gradient. Please don't mix up variables and constants. In video 1.2, we did a little real-life example of looking at monthly cell phone charges, and we said if it's 2 Rand per minute, then the graph of your bill in rands versus your time in minutes will just be a straight line with a gradient of 2. The y-intercept will be 0 because there's no initial charge. Now, we showed you in that video that that's a good analogy to Ohm's law. Current in amps is your dependent variable. Voltage in volts is your independent variable. And then the gradient is given by 1/R. So a large resistor will have a small gradient, and a small resistor will have a large gradient. If it's an ohmic conductor, we expect that C is equal to naught, and current is directly proportional to voltage. So once again, we need to compare the mathematical graph with the Ohm's law graph. And in the next video, don't worry about it now, we'll look at the internal resistance graph, which you'll see looks a little bit different. Again, the examiner stressed, learners must be taught how the equations in physics are related to the equations in mathematics. So we compare our variables from the mathematics to Ohm's law and our constants. Now, one of the other things that the examiner stressed is, although the principles of series and parallel circuits are taught from grade 9, the basic principles have to be revised and practiced constantly. The critical features of series and parallel circuits should be reinforced, and the examiner himself recommended that PHET simulations are used. So that's exactly what we're going to do next. We're going to revise our series and parallel circuits by looking at the PHET simulations. So noting the importance of series and parallel circuits, let's turn in our booklets to pages 24 and 25. On those two pages, there's a summary of series and parallel circuits. Starting on page 24, a very simple series circuit, 3 resistors in series with an ammeter and a battery. In the middle of that, you will see a circuit that we've built up using the circuit construction kit, which comes with PHET. And we'll go to that in a moment so that we can test these theories that we have about series circuits. Lower down on page 24 are 6 notes about series circuits. And again, these will make a lot more sense when we test them using PHET. So we'll get there in a moment. On page 25, we have a parallel circuit. Again, the simple circuit diagram, 3 resistors R1 to R3 in parallel with each other, but in series with an ammeter and a battery. And again, next to that, we have set up the equivalent circuit in PHET in the circuit construction kit. This is followed by, again, 6 notes about parallel circuits. Now, what's going to work best for you is actually if you open up your books wide, don't fold them over, so that page 24 and 25 are next to each other, because it really helps to compare the notes for series and parallel circuits. And in most cases, you will find that they are exact opposites, and those contrasts should help you to remember them. So you keep your booklets open, and I'm going to go to the PHET simulation. We will test these things in reality. So here we are in this great simulation, the circuit construction kit, the DC version. There's also an AC version that we'll use later to look at question 9. Again, teachers, the simulation is in your teacher pack, so please take the time to explore it by yourselves. It's really easy to use. I have completed the circuits beforehand to save time, but you can see, for example, if I remove that wire, I'll show you how easy it is to build it. You simply take a wire, drag it into place, and join the ends like that. So we have the simple series circuit on the left, as you see on page 24, and the parallel circuit on the right, as you see on page 25. We can also click here to represent them as circuit diagrams, but I think that we will learn more by looking at the pictures here. Now, at the moment, both ammeters show 0 amps because the switches are open. If I close the switch, you can see it reads 0.33 amps. If I close this switch, we get a much higher current. In fact, it's 9 times as high, and it reads 3 amps. Now, we've carefully chosen the values. We've got 2 10-volt batteries, and we've got 10 ohm resistors, so that it just keeps calculations easy. But just note the most important thing, that all the resistors have exactly the same value of 10 ohms. Now, you can see from the ammeter that a current is flowing, but actually a much easier way to see it is to take a look at the actual current. And you can see what it does here is it shows you the electrons in the wire. And if I switch the switch on, you can see the electrons start to move. And you can see in the simulation how much faster they move in the main circuit of the parallel branch because the current is 3 amps. Remember, current in amperes is coulombs per second. So if you literally counted how many of those charges passed you per second, that is a measure of current. So this shows us very nicely, and if I turn the switch off, then the movement of electrons actually stops. Now let's go through points 1 to 6 on your page 24 and 25, and we'll do each point for both circuits together for comparison. So point number 1 on page 24 says a series circuit is a straight or unbranched circuit. So you can see there are no choices. Every one of those blue electrons must pass through every part of the circuit. Parallel circuit on the right is a branched circuit. And you can see at that point there that I'm showing you, that is actually a junction. It's like a fork in the road. And the electrons can decide if they're going to go up or straight or down. And that's very important because it's branched, there is some choice. Now this affects point number 2. Point number 2 says because all the current has to pass through every resistor, if I remove one resistor like that, you can see the current stops flowing. Ammeter reads 0 and the electrons are no longer moving. And with the resistor back in, the current is flowing again. Let's look at the parallel circuit. If I take that resistor and I remove it, you can see the current continues to flow. Obviously, there's no current in the top branch now, but it has two other options. And that's why the current doesn't stop flowing. This is why this is much better for something like household lighting. Otherwise, if one bulb goes out, all of them go out. I can even remove another resistor. And again, the current continues to flow through the bottom part. You will see on the ammeter, the current has got less, but the circuit has not been completely broken. Now, point number 3 is about what happens with the resistors. And it says that in the series circuit, when you add resistors in series, you increase the resistance and you decrease the current. Now, the easiest way to do this is I'm actually going to connect 2 extra wires there. And if you look carefully, you'll see that that first wire has effectively taken out R2 and R3. So if you look at the flow of electrons, they're now only flowing through R1. So you can see the current is going quite fast, and the reading on the ammeter is 1 amp. If I take that wire and I remove it, you'll see immediately the current drops to 0.5 amp because it's now passing through 2 resistors. So by adding a resistor in series, we've increased the resistance and decreased the current. Let's do that again. Remove that extra wire, and now the current has dropped to 0.33 amps, and you could see how much it has slowed down, because it has to pass through all 3 of the resistors. In the parallel circuit, we'll do it in a different way. We've got 1 resistor. The current is 1 amp. Let's add a second resistor. You can add that in here, join it up, and you can see the current is actually increased to 2 amps, and you can see the electrons are moving faster because those electrons have an option, so you don't get such traffic jam of electrons trying to get through 1 resistor. Let's add a third resistor. Remember, the current is 2 amps. Add our third resistor, connect them up, and you can see the current is now 3 amps. So adding resistors in parallel increase the current. Adding resistors in series decrease the current. Point number 4 is about how we calculate equivalent resistance. We prefer to say equivalent rather than total, because total would include the resistance of the battery, the ammeter, the wires, and everything else. So the equivalent resistance of those 3 resistors, R1, R2, and R3, is what resistor you would need to replace them. So here you simply add up R1 plus R2 plus R3. Let's put the values back. The equivalent resistance of those 3 is actually 30 ohms. That's why 10 volts divided by 30 ohms gives you a current of 0.33. Here, you calculate it with a slightly more complicated formula that you'll see on page 25. And in fact, the equivalent resistance of these 3 is actually 10 divided by 3, which is 3.33 ohms. And that's why 10 volts divided by 3.33 ohms is equal to 3 amps. Let's look at point number 5, which is about the total current. Now we have a fixed ammeter in each side, but we're going to use this non-contact ammeter. All we need to do is put it over the wire or the ammeter, and it measures the current passing through. Now, the point with the series circuit is it doesn't matter whether you measure current on the left or on the right or at the bottom or in the battery or in any of the resistors, you can see we get exactly the same current passing through. I think it makes sense. Point number one says it's an unbranched circuit. So because all the electrons have to pass through every part, the current has to be the same everywhere. Now, the same is not true for the parallel circuit. Current through the battery and through the ammeter is 3 amps, and through the main part of the circuit is 3 amps. But you can see that the current splits here. And of those 3 amps, you can see 1 amp goes through the top branch, 1 amp through the middle branch, and of course through R2, and 1 amp through R3. That's why we call this a current divider. When the current gets to that point, the 3 amps divides up, 1 to the top, 1 to the middle, and 1 to the bottom. What about voltage? Let's get our voltmeter out. If we measure the battery voltage in the series circuit, you can see it's 10 volts. But if we measure the voltage across just one resistor, you can see it's 3.33 volts. That's why we call this a voltage divider. The total voltage of 10 volts is divided up between the 3 resistors, and each one gets 3.33 volts. So 2 resistors with 6.67 volts, and across all 3 resistors, of course, the voltage is the same as the battery voltage. Now, again, that is not true for the parallel circuit. We can measure the battery voltage here, and we get 10 volts. But if we measure the voltage across resistor R1, instead of getting 3.33, we still get 10. If we measure across R2, we still get 10, and if we measure across R1, we still get 10 volts. So it doesn't matter. Each of the resistors enjoys the full battery voltage, and that's why in a parallel circuit, if you have light bulbs, that's why they would shine so brightly. Now, so far we've looked at a simple battery with no internal resistance, but you can see using this app, you can give the battery an internal resistance. The value will now show that this battery has a 2 ohm internal resistance. So if we measure the EMF with no current flowing, we get 10 volts on the voltmeter. But if we close the switch here, now we actually measure the terminal voltage as a current is flowing, and you can see that there has been a voltage drop. But we'll talk more about that in the next section. So to finish off with pages 24 and 25, let's talk a little bit about the equations which come into this electricity section. These are found on page 39 of this booklet in your data sheets. First of all, on page 24 at the bottom, we have the equations for electrical work and power. The main difference is that power is equal to work divided by delta T. So you'll see all these equations on the left change from work to power simply by dividing by delta T. Very simple. Easiest one to remember is just that power is equal to voltage times current, V equals VI, and one uses Ohm's law, V equals IR, to get these other forms of the equation. All these 8 equations are given to you in the exam, so just make sure that you know how to use them. And this wheel is an interesting way of calculating different variables. At the bottom of page 25, we remind you about Ohm's law. It's often written as V equals IR, but in fact, the form in your data sheets is R equals V over I. It's dealing with 3 variables: resistance measured in ohms, potential difference or voltage in volts, and current in amperes. And these triangles show you the different ways of calculating and changing the subject of the formula. This little diagram might be helpful in understanding the units. So ohms measures the amount of squeezing that takes place. Volts measures the amount of pushing that takes place. And amperes is a measure of the flow of the current. So don't forget about series and parallel circuits rules. But let's go straight to page 20 and look at Ohm's law. Now, again, we're not going to try to recover all the theory or do lots of circuit calculations. We're going to focus on the experiments and the graphs for Ohm's law and for internal resistance on page 20. Now, the aim of this experiment is simply to investigate the relationship between voltage and current. When we have a circuit set up like this, it's a very simple circuit. We have a resistor with a voltmeter in parallel across it, and an ammeter in series with it, and a battery or some sort of power supply. Ohm's law is often written V equals IR, or I equals V over R. And in this case, we're going to look at the fact that V over I is constant, and it's equal to the resistance. And that's the form of the formula on your data sheets. Now, again, this might look trivial and too easy, but the examiner last year commented learners are unable to substitute the correct values of R, V, and I when applying the formula R equals V over I to the whole circuit or to parts of a circuit. So this is important, and we need to understand the direct and inverse relationships. And we're going to do that by having a look at another PHET simulation, this one called Ohm's law. Now, this is a very simple simulation. We have Ohm's law in the form V equals IR, and we can change the values of voltage and resistance and see how that affects current. So current is going to be our dependent variable. Now, the simple one is if we increase the voltage, you can see that's by adding batteries. As the voltage increases, so the current increases. As the voltage decreases, so the current decreases. They are directly proportional to each other. Now, what about the resistance? At the moment, we've got a small resistance. As the resistance increases, you can see the current decreases. They are inversely proportional to each other. They've shown the resistance increasing in the resistor here. And as the resistance decreases, then the current increases. So resistance and current are inversely proportional to one another, whereas voltage and current are directly proportional to one another. Please understand those relationships. How are we going to do the experiment? Well, we're setting up the circuit with a simple circuit diagram on the right here. We're not actually going to use batteries. We're going to use a DC power supply, because by turning the voltage control, we can very carefully control the voltage, which will be our independent variable on the x-axis. In other words, we decide what values the voltage will have. Now, there's various ways of measuring current and voltage. You can get analog voltmeters and ammeters, but I want to recommend to teachers rather to get digital multimeters. You can get them from hardware stores. They're inexpensive. They can be set up as voltmeters or ammeters, and they take the normal banana plugs. So they're very useful. Notice that the ammeter is in series with the resistor. Ammeter always has very low resistance. The voltmeter is in parallel, and it always has very high resistance. Now, I'm going to use the Pasco Capstone software because it just enables me to do things in real time on the screen for you. So notice the ammeter will be reflected by a digital ammeter readout that will be put onto the table in the left-hand column, and it'll be graphed as the dependent variable on the graph. The voltage, the voltmeter, will be represented by this digital voltmeter readout. It'll be the right-hand column of the table and will be the independent variable on the x-axis of the graph, just so you know what you'll be looking at when we do the experiment. Now, on page 20, you have this table, and you are going to fill in the data as it comes up, do the calculations of the two right-hand columns, and draw the graph yourself. What you can do immediately is fill in the potential difference readings, as we've decided before the experiments that we're going to use 0 volts, 1 volts, all the way through to 5 volts. So we're going to do the experiment for Ohm's law, and this is the experiment which you'll find on page 20 in your booklets, and you're going to fill in the graph which is on page 21. Now, I want to stress that this is a real live experiment. This is not a simulation. I could, of course, use these multimeters for ammeters and voltmeters, but instead I'm going to use this Pasco voltage current sensor that allows the voltage and current readings to be fed directly into my computer. I have a resistor here. It's a resistor that looks like this one, just a simple ohmic resistor, and we have a voltmeter connected across it in parallel and an ammeter connected through it in series. Instead of using batteries, I'm going to use this DC power supply, which gives me a very stable DC voltage, which I can set as I want it. So we've connected to the capstone screen within the Pasco software. And again, just to stress that what you see on screen is not a simulation or a picture. We're going to get actual experimental readouts. We've got a digital ammeter, a digital voltmeter. We've got a table similar to your graph on page 20. And in fact, as we get readings, you can copy them into your table on page 20, current and voltage. And we're going to be drawing a graph of current in amperes versus voltage in volts. Please note that voltage is the independent variable. I'll be directly changing the voltage by turning the knob on the power supply here. I can't directly alter the current, so current in this case is dependent on voltage. It's very important to have those two correct here. When I switch the system on, I want you to see that it's actually taking live readings. And as I increase the voltage, you can see the voltage and current increasing. And you can see on the graph, it seems that we have a linear directly proportional relationship. But of course, we want to test that. And we want you to be able to draw the graph yourself. Notice that the values in the table here are live. They're changing. And when we get to the voltage we want, I tell it to keep the sample. So we have a reading for 0 volts and 0 amps. I'm going to turn it up to exactly 1 volt. And I'm going to tell it to keep the sample. So it has kept a reading of 1 volt with a current of 0.1 amperes. I wonder if you can guess what the resistance is yet. So I'm going to turn it up to 2 volts. Carefully. And we get a current reading of 0.21 amperes. Turn it up to 3 volts. Current reading is 0.31 amperes. Turn it up to 4 volts, 0.40 amperes, and turn it up to 5 volts. And we get 0.51. We're going to stop it there because we're just going to take 6 readings for now. Of course, the scientist would want to take far more than that, but because of time and space, we're just going to take 6. Now, maybe some of those readings weren't exactly what you thought they should be, but please note we're doing an experiment. So we write down our actual observations, not what we would like them to be. So these are actual experimental results. So that is our first set of 6 readings. And those are going to go in the first 2 columns on your page 20 under potential difference and current for the resistor. Now what we're going to do is we're going to actually change, we're going to take the resistor out. You can see me doing that. And I'm going to replace it with a light bulb here. Now, light bulb is also a resistor, but we're going to find that it possibly doesn't show Ohm's law quite as well. And if I turn up the voltage here, you can actually see the light bulb glowing. So that's how we'll know that the light bulb is on. We're going to continue exactly the same experiment, but just this time with the light bulb instead of the resistor. So we will ask our graph to be able to show all the readings which are there, and then we're going to start a new set of readings here. Okay, so once again, I'm adjusting the voltage here because voltage is our independent variable, and it starts off 0 volts, 0 amps, just like we found before. I'm going to increase the voltage up to 1 volt. Just allow the current to stabilize. And we can see already the current is less than it was, and the graph is below what it was before. Increase to 2 volts. Again, just allow the current to stabilize. You can see now the current is quite a lot less than it was before. Increase our voltage to 3 volts, 0.11 amps to 4 volts. You should be able to see the bulb just glowing, 0.13 amps, and finally to 5 volts. 0.15 amp, and we'll stop the recording there. So remember the blue graph at the top, that run number 1, that was for the resistor, and the red graph at the bottom, that was for the bulb. You can see the bulb glowing here, and we see we get quite a different picture. Obviously the resistance of the bulb is greater, but also we see we don't get a nice straight line for the bulb like we got for the resistor. Now, having finished with all our readings, I've just made the graph a little bit bigger so that we can see it. And again, the blue graph, run number 1 was for the resistor, the red graph, run number 2 for the light bulb. Now, let's focus on the blue graph, which looks like a nice direct proportionality. And what this great software allows us to do is to put a best fit line on it. So we're going to choose a linear best fit line, and you'll see that we get these figures here. Now, they use slightly different notation to us, but we've got a current equals mV plus B. So the gradient here, we've got 0,102. And the B value, which we expect to be 0, you can see it's very, very, very tiny, 0,001 negative. So it's as good as 0. It's really tiny. Now, what does R mean? This is not internal resistance. This is something called a regression coefficient. And it's a statistic which tells us how accurately our points lie upon a straight line. And you can see R is equal to 1 tells us that we have an almost perfect fit here. So we can say with great confidence that current is directly proportional to voltage as long as the resistance is constant and as long as the temperature doesn't change. If we look at the second one, it's definitely not a straight line, and we wouldn't be able to say the same for the non-ohmic conductor. So let's make sure that you've got all the values that we obtained in the experiment. First of all, we did run number 1, which was for the resistor, and these were the values which were obtained. I've just enlarged the table on the left. If you haven't had time to copy them down, then the teacher should just pause the video at this point until everybody's got all those values down. Run number 2 was for the light bulb, and we saw the larger resistance and the non-ohmic response. These were the values which were obtained for number 2, along with number 1. And again, if you don't have all the values down, please just pause the video. Pupils should also complete the 2 right-hand columns to calculate V over I for the resistor and for the bulb. So please pause and complete those columns before continuing further. So the table on page 20 should be completed now. Let's turn to page 21 and let's do the graph. And first of all, we're going to construct this graph by using the Tulsip method. So the first T stands for title, and we've already put a title to the graph, current versus voltage. Just make sure that what's on the y-axis, current, is mentioned first, and what's on the x-axis, voltage, is mentioned second. Secondly, A is for axes. Choose a variable for each of the axes, and L, label your axes with units. So if you haven't done so, fill these into the boxes on the side of your graph. Current on the y-axis, voltage on the x-axis. Now, this causes some confusion. Let's clear it up. Scale. There are 11 large blocks on each axis. So we need the data again so we can have a look at it. So let's start with the x-axis for voltage. So we can fill in their voltage ranges from 0, that's the lowest reading, to 5 is the highest reading. Now we've got 11 blocks on each axis, so we can use 10 of them, and 5 divided by 10 is 0.5. So we're going to fill in our voltage readings. Basically, a small block is 0.5, sorry, a big block is 0.5, 2 big blocks is 1. And so that's the scale for voltage. Now, you'll see that the current readings are very different. They're about 10 times smaller. So we need to put there that on the y-axis, current ranges from 0 to 0.5. So in this case, one large block should equal 0.05 amps. So look at the scale for the current axis. You can see it's quite different here. Now, apart from scale, we need to carefully consider the intervals, because inside a large block, you can see there are 5 small blocks. So how much should each small block represent? Again, let's start with the x-axis. One large block equals 0.5 volts, and there's 5 small blocks inside, so each small block should be 0.1 volts. So each one of these little blocks represents 0.1 volts, and there are 10 of them which make 1 volt, which is quite easy. On the y-axis, one large block equals 0.05 amps from there. Dividing by 5, each small block should be 0.01. So on the y-axis, one of these small blocks is 0.01 amps. Now, your graphs will very often have different scales and different intervals on the X and Y axes. So don't assume they're the same, but by choosing these scales, you can see our graph will fill the whole page, which is what we wanted. Next, we're going to plot our data from the table onto the graph carefully, and then plot the best fit line for the data points, calculate intercept and gradient. Now, I'd really like you to do this at this point. So I'd like to ask you to pause the video, take this data table from page 20, and carefully plot the points onto the graph, and then try to draw your best fit line and calculate the intercept and gradient. Try this before proceeding. So I hope you have plotted the graph yourselves to get practice, because this is a skill which you may be called on to do during the exam. So here's the data table that we need. And going across, it's very simple because we're using whole numbers of volts. So all the points will fall on these big, thick lines, which makes life easier. Now, it's going to be difficult for you to copy this from the screen exactly, but basically our green points for the resistor will lie like that: 1 volt, 2 volt, 3 volts, 4 volts, and 5 volts. We notice they lie almost perfectly along a straight line, indicating that current is directly proportional to voltage for the resistor. For the bulb, I'll quickly put those points in. It's a different story, and you can see it's actually curving away like this. Because the bulb gets hotter, it doesn't obey Ohm's law. So I hope that your graphs look like that. And it's important to be able to use the scales and the intercepts to put points in the correct place. Now, we apply a best fit line, and we're not going to bother to do it for the bulb because it doesn't lie along a straight line. A couple of points with the best fit line. Please don't play join the dots and make a jagged line. It must be a single straight line, and it must be the line that lies closest to all of the dots. Don't just connect the first dot to the last dot and ignore the others, but try to find a line which lies closest to all the other dots. Here it can be useful if you have a transparent ruler, a see-through one, so you can see the dots on either side. And that best fit line will help us to find our gradient and intercept. Now, I hope you've done these calculations, V over I for the resistor and the bulb. We can see for the resistor, they were almost perfectly constant. Only the third decimal place changed, whereas for the bulb, they were very different. And so we definitely didn't get a constant reading for the bulb. So let's do our conclusion at the bottom of page 20. And we will need these figures, and we will need our best fit curve for the resistor. But we can fill in there the ratio of V over I was constant for the resistor. Now, you might say they're not perfectly the same, but really within the limits of this experimental accuracy, they were almost exactly the same. This indicates that the conductor used was an ohmic conductor. It obeys Ohm's law, and the resistor used had a resistance of 9.8 ohms. Now, where do we get that from? Well, we calculate the gradient, and remember the gradient is 1 over R. So R is equal to 1 over M, and 1 over 0.102 gives us 9.8 ohms. You could calculate the gradient from your straight line, or you could just take an average of all of these V over I values, which is in fact is 0.102. So this concludes our Ohm's law experiment. And in fact, when we analyzed the graph on the Pasco software, we saw that the experiment went very well. We got a very good regression coefficient, and the points lay nicely along a straight line. And this confirms that indeed the gradient, which is 1 over R, is 0.102. The y-intercept is very, very, very small. It's effectively 0, which we'd expect for a direct proportionality. As always, we would like to relate what we learned in the experiments to the questions you can expect in the matric exam. And I guarantee these questions will be easier to answer because you've done the experiments. So let's have a look on page 22 and 23. There's 2 Ohm's law questions, one for 8 marks and one for 9 marks. That's 17 marks together. So if you haven't tried these yet, it's very important that you do try them on your own. Please pause the video here for 17 minutes. That's how long it should take you. while you try to complete these two exam questions on page 22 and 23. Please pause now. Right, and let's look at the answers. These were actually not too difficult. Here's your graph. It's a standard Ohm's law experiment, just like we did, and a graph has been drawn of current on the y-axis versus potential difference on the x-axis. 911 asks, what is the independent variable? That's always on the x-axis, so that is potential difference in volts. 912, write down the variable that must be controlled. Well, of course, the resistance must be constant and temperature must be controlled, either one of those. 913, what is the conclusion that can be obtained from the graph? Well, it's a straight line through the origins. The conclusion is that current and potential difference are directly proportional. Or you could say that the resistor is an ohmic conductor. 914, using the gradient of the graph, calculate the resistance of resistor P. Well, the gradient is delta Y over delta X, and we calculate the gradient. Where did I get that from? The Y value of the gradient is from there to there. It's 0.18. Now, what you learned from TALSUP about scale and intervals is very important here. Each small block in the vertical is 0.02 amps. So 9 of those small blocks is 0.18. And with a voltage, it's very easy because that lies right on the line. And that's why I chose these two to calculate the gradient. Resistance is 1 over the gradient. And that'll be 1 over 0.36, which is 2.78 ohms. So that should have been 8 easy marks for you. Let's look at page 23. This is a bit more interesting because the graph is straight up to that point, and then you can see it bends. Now, we saw this when we did the experiment for the light bulb, which did not obey Ohm's law. This one appears to obey Ohm's law to a point, and then it actually deviates from that. Once again, an easy question, 9.1. Which one of the measured quantities is the dependent variable? Dependent variable is always on the y-axis, so this is simply the current. 9.2, the graph deviates from Ohm's law at some point. Well, that point is simply the point over there. You can see a break in the line, and that has coordinates 4 volts and 0.64 amps. So those are the coordinates. Always give x first, followed by y. Now, notice again, how do we know that's 0.64? Between 0.6 and 0.7, there are 5 blocks. So therefore, each block is 0.02, and 2 of the blocks will be 0.04. That's how we know it's 0.64. Those coordinates are important. 922, give a reason for the deviation. Well, we expect that there was a change in temperature, and temperature must be constant for Ohm's law to be obeyed. 9.3, calculate the gradient of the graph for the section where Ohm's law has been obeyed. Now we have an advantage. We already know the coordinates of that point, and that will make it easy for us because delta y is just from 0.64 down to 0, and delta x is from 4 down to 0. So it's very easy. We already know the coordinates, and the gradient is 0.16, so therefore R is 1 over the gradient, which is 6.25 ohms. So I hope you've seen how performing the actual Ohm's law experiment and understanding the data analysis and the graphs really helps you to answer exam questions. You will see from the dates of those 2 Ohm's law questions that they haven't come up in the exams for quite a few years. Nevertheless, being able to draw graphs from the Ohm's law experiments is a very useful way of helping you to understand electricity. Let's have a look at one more question 8 example, which is not in your booklet, so just pay attention to the screen. There is always some circuit analysis which happens in question 8, whether there are graphs or not. And we're going to look at a question from the September 22 trial exams, which were in KZN. It's not in your book, so just pay attention on the screen. This was an easier question in that there was no internal resistance. So it was really just a question which tested knowledge of Ohm's law and series and parallel circuits. and the power equation. So you've got a simple circuit with 4 resistors connected, some in series, some in parallel, and there's various calculations which are asked of you. Again, 8.1, state Ohm's law in words. That is straight recall, so I'm not going to do that one. Now, of course, you need to go straight to page 39, your equations and the circuits and internal resistance equations. You're going to be focusing on these ones, Ohm's law and the series and parallel equivalent resistance equations, and also for 823 and 822, your power and work equations there. But they're all given. You can ignore these internal resistance equations because you're told that this battery does not have an internal resistance. So let's start with 821, total current delivered by the battery. And we know the voltage of the battery, and from Ohm's law, in order to find the total current, we need to find the equivalent resistance of all these resistors together. So we can start at the top and say the equivalent resistance of these two at the top, they're in series, so you just add them to get 18 ohms. Then you effectively have an 18 ohm and a 12 ohm resistor in parallel. So we use our equation 1 over R parallel is 1 over 18 plus 1 over 12. Do it carefully, and you get an equivalent parallel resistance of 7.2 ohms. Remember, that should be smaller than either the 18 or the 12. Then there's one more resistor in series, the 4 ohm, and we simply add that to 7.2 to get a total resistance of 11.2 ohms. So total equivalent resistor of the whole circuit. In other words, if you took away all these resistors and put in just a single 11.2 ohm resistor, the circuit would function the same. So the current is just V over R, 12 over 11.2, 1.07 amps for 5 marks. Now, it's actually easier to do 8.2.3 next because it asks about the total energy used if the current runs for 30 seconds. Now, I'd suggest you use VI delta T, although there are different equations you can use because we know the voltage is 12 volts. We know the total current is 1.07 amps, multiply by 30 seconds, and we get 385.20 joules. So I think it's easiest to do that question next. And then 822, the power delivered to the 10 ohm resistor. I'm going to leave you to do most of this calculation, but basically you can use power equals I squared R. So you need to calculate what the current is passing through the top branch. You know the total current is 1.07 amps. You know that more of it will go through the smaller resistance, but I'll leave you to calculate that the current passing through the top branch is 0.43 amps. Multiplied by 10 ohms, and we get a power of 1.85 watts delivered to the 10 ohm resistor. The last question says, if you remove the 12 ohm resistor, how will that affect the total current calculated? Now let's remove the 12 ohm resistor. In fact, by removing a parallel branch, the total resistance becomes more because we now just add them. 4 plus 10 is 14, plus 8 is 22 ohms in total. So the current decreases because the total resistance increases, and resistance is inversely proportional to the current. They often ask a question like that, what happens if you remove a resistor? Now, it's good to do the theory, but I showed you before the fantastic circuit construction kit for DC circuits, which is provided by PHET. And it's so accurate. You can see what I've done here. Here's the exam question on the right, and I've set up the circuit so it exactly matches. A 12-volt battery, the resistances are all the same, all the branches are the same. So we can actually take voltmeters and ammeters, and we can measure the things that we have been calculating. So, for example, our voltmeter is measuring 4.29 volts across that 10 ohm resistor. Our ammeter, remember, it's a non-contact ammeter. By just holding it over the wire, it shows the current flowing through that wire. So, for example, 8.2.1 says what is the total current, and you can measure it there to confirm your calculations. 8.2.2, what is the power through the 10 ohm resistor? It's just I squared R. We've put in an ammeter there measuring the current of 0.43 amps times 10 for the 10 ohm resistor, 1.85 watts. And finally, what is the amount of work done in 30 seconds in the main circuit? Well, 12 volts times 1.07 amps times 30, which is 385.20 joules. Now, what I'm showing you here is just a screenshot. In other words, it's not working. But let's now go to PHET and let's actually do the circuit live and show you how you can get these same values. And I really encourage you to try it for yourselves. Teachers, you all have a copy of the software with what we've given you. So this is not just a screenshot, as you saw in the last two screens. This is the actual live simulation on PHET. You can see the switch is open, and when I close it, you can see the electrons move and the circuit functions here. Now, let's grab an ammeter. This is a non-contact ammeter. So by simply moving the detector across the wire, it can measure the current. And there you can see the 1.07 amps as we calculated coming out of the battery. Now notice, of course, on the side branch, it's also 1.7 amps, but then it meets a junction. If you look carefully, you'll see the electrons are flowing faster in the main circuit than they are in the branches. So let's check. Through the 12 ohm resistor, the current is only 0.64 amps. And through the top branch, the current is only 0.43. But of course, if you add those two together, 0.64 and 0.43, you get the 1.07 amperes. Let's check voltages because we can also measure that. And of course, the voltage across the battery, just need to get it accurately here. Voltage across the battery is 12 volts. Now, if we measure the voltage across the 12 ohm resistor, because there's this 4 ohm resistor, it's less than that, 7.71. And you see, just by moving these probes, we can accurately measure the voltage at any point in the circuit. Now, let's have a look at the last question, which said, what will happen to the current coming out of the battery if we remove the 12 ohm resistor? And we decided that that current should actually decrease because the resistance increases. Let's see if that's true. 1.07 amps. Let's take the 12 ohm resistor, and I'm going to remove it. And you can see the current drops to 0.55 amps. In fact, we can see that the current has slowed down here. Fantastic simulation. Please take time to use it. It's available on either website, and you really will learn a lot more about Ohm's law, resistors in series and parallel. Although this battery has no internal resistance, you'll see that I could very easily change the internal resistance of the battery, so I can also learn about that. So that's the end of this video on Ohm's law and circuits. Apart from preparing you for your matric, this knowledge is so important in everyday life because we're so dependent on electricity in our homes. Once again, I encourage you not to go away, but to stay watching for a fascinating interview with someone who handles the enormous voltages and currents which South 32 uses to make aluminium. So I'm delighted to be able to speak with Mongezi Sotsaka, who works at South 32. Mongezi, welcome. Tell us a little bit about yourself. Where are you from and what did you study?
Okay, thanks for having me, Derek. So my name is Mongezi Sotsaka. I was born and raised in the Free State. And then when I completed matric, I moved to Johannesburg to do my electrical engineering degree at the University of the Witwatersrand.
Okay, so you did electrical engineering. Now, you're aware that this is a module I've just presented on electricity. Tell me how you're involved with the electrical side of South 32. Where do you work there?
Okay, so currently I'm the superintendent for substations and utilities, meaning that I'm in charge of making sure that there is electrical supply to the plant and that all the plants have electricity and that the equipment that ensures that we have electricity is well maintained.
So it sounds like a lot of problem solving, and this video series I'm presenting is all about problem solving and skills rather than just learning content. But I mean, tell me, you still remember your matric electricity? Is it relevant? Is it important to the job you're doing now?
Very much so, very much so. So as you get higher and higher, yes, there's specialized fields of electrical engineering where you focus on stray currents and inductance, and all these specialized fields, automation, instrumentation, which is like the electronic side of things. But on your HV power, it's very basic principles. It's your V is equal to IR, your power equations, P is equal to I squared, R, just those simple equations that actually help in solving problems when you then get into the plant. So definitely a good foundation, you get a very good foundation from your metric science, the circuit portion of that. You'll definitely get a good foundation thereof, and also the chemistry side of things too, because you have things like deionized water, where you want water that will actually cool your systems, but it actually does not conduct. Now that's where a basic knowledge in chemistry also comes in and assists. Yeah.
Sure. So I've been presenting problems where they have a voltmeter reading 5 volts and maybe a current of 1 amp flowing. Tell me about some of the voltages and currents you're dealing with in the plant.
So yes, interesting part. So our input voltage, the one coming from Eskom, is 132,000 volts. So wow. in technical terms, you actually say 132 kilovolts. Okay, so that's the input lines coming in, which via a transformer we step it down to 22 kilovolts, so 22,000 volts, and then further down all the way up until we get to 400 volts. Okay, and then further even down to 220 for your plugs and so on.
Sure.
So that's the range of voltage that we have on the plant, from 220 all the way to 132,000 volts. So that's the AC side. On the DC side, we also have DC equipment, which then outputs a voltage of 1,235 volts DC. But the interesting part is in the current that it outputs. So it outputs 362,000 amps. Yeah,
direct
DC,
current.
which is
wow.
Direct current. Yeah, 362,000 amps. Yeah, so 362 kiloamps. So yes, that's the interesting part, sure. And that's what gets into the pot lines. Yes.
Yeah. I mean, we're teaching about the fact that probably in your house, the thing that uses the most current is a stove that maybe runs off 40 amps, and you've got 300,000 amperes. So, we teach at school about the magnetic field of a current carrying conductor. Do you remember that? And so this must be one of the biggest magnetic fields in the world.
Yes, a lot of things. So if you go in there with your credit card, I'm sorry, you're going to have to go to the bank and request a new credit card. Sure. If you go in there with a clock, not a non-digital clock, yes, you probably will have to reset your watch again because it will just freeze in one spot. So definitely, and then the most interesting part, when I moved there, you could have keys in your pocket, and you'll actually feel them pull you towards these bus bars and these conductors. So it is quite an interesting experience there.
Wow. Well, Mongezi, thanks so much. Just in closing, it's good to hear you confirm the fact that matric maths and science is so important.
Not about how many times you fall, but how many times you get up. That is actually where true character is defined. So you may have had a tough year, a year that was disturbed, and it was not like the previous years and so on. But if you hang in there and you determined to make something of yourself and to succeed from this year, there'll be very little that you'll come across in your later years of life, that will not that will actually beat you. There'll be very little that you will not be able to overcome.
Mongezi Sotsaka from South 32, thank you so much for this.